If you remember yesterday, I gave the example of like a baseball bat. We're going to take like a lathe, or at least that would be one way to create something like this. And the cross section of this figure, of this shape or this solid, is going to be a circle, perpendicular to some axis. So if we rotate it around some axis, it's going to create cross section circles or circle cross sections. So here's the example I want to look at. What we're going to do here, first of all, when we're doing these problems, I'm always going to draw the axis of revolution and just draw a little arrow around it. So what we're going to do is we're going to take this region right here, this region, and we're going to rotate it around this axis. And we're going to end up with a solid. Now, can anybody just describe really quickly what that solid is going to look like? It's going to look a little bit like an M&M or maybe like a squished football. So a football is kind of an oval shape. If you squish it so that it's fatter, it might look something like that with the points here and here. So if we take this shape and we revolve it, we're going to get some sort of ball, but not a spherical ball, if you will. So what I'm going to do here is I'm going to use Riemann sum rectangles. I'm going to split it up. I'm going to slice it up. I'm not going to slice it up into infinitely many pieces, but just a finite number of pieces. It really doesn't matter how many I have here. It's an arbitrary number for now. Eventually, we're going to take this number. We're going to let that number go to infinity, so we have infinitesimally small slices, and we add up the volumes of each of the slices. So if I take just one of these rectangles, I'll just use a left-hand rectangle. Remember, this is just an approximation method. And I'm going to take that rectangle and I'm going to rotate it around our axis of revolution. What am I going to get when I rotate that rectangle around the x-axis in this case? Yeah, it's going to be a cylinder. It's going to look something like that, right? Now, it is a cylinder. We're going to call it a disk. And we're calling it a disk because of its thickness. And the better our approximation is, we better our approximation by making the disks narrower or smaller. So it looks more like a disk than like a cylinder. But really it is a cylinder. So to find the volume of this disk or this cylinder, what are we going to do? Let me... What is it? Okay, so the volume of this thing is going to be the area of the base times the height. And let's just put this in the context of the problem then. The height, in this case, in the example I just gave you, is going to be what? That's going to be delta x. Okay, so the thickness of this thing is going to be the change in x. And remember, we want delta x to get so small that we start calling it a differential. We call it dx. The area of the base depends on the radius of this circle. So I'm going to look at this orthogonal projection here. We'll call that r. And the area of that base is going to be what? Pi r squared, yes. So that means that this volume here is going to be the area of the base, pi r squared, times delta x. Pretty straightforward, right? Now, that's just the volume of one slice of this thing. What we want to do is we want to add up a bunch of slices. So when we do that, we're going to get a bunch of disks stacked on top of each other, stacked side by side, however we're slicing it up, and we want to add all of those up. So the volume of a lot of disks, I only have 4 of them pictured here, but you could picture, I don't know, infinitely many of them maybe. Okay, maybe not infinitely many, but a lot of them, hundreds or thousands of them. So the volume of a lot of them is going to be the sum of those areas, pi times the radius squared times delta x. And this right here is a Riemann sum. It's an approximation of a total volume. I want to point out one thing about this sum. I don't have limits on my sum. I don't have I equals 1 to 12 or I equals 1 to 4 actually would be more appropriate for this example. But this delta x here, the r here, Those are going to depend on what our limits on the sum are, and we'll kind of take care of that when we move into the integral. So the limits on the sum don't necessarily translate to the limits on the integral. In fact, they really don't. The limits on the sum are really telling us how many, in this case, how many disks we're adding together. I'm leaving those off because they're not really important. That's kind of a details thing that we don't really need. We're just looking for the main idea here. So what we're going to do is we're going to take this formula, and when we let delta x get really small by increasing the number of disks that we use, this is going to turn into dx, and so this volume here is going to become an integral. So the exact volume, not the approximate volume, but the exact volume is going to be the integral of pi times the radius squared with respect to x. And here are limits from a to b. Those are going to be the limits that we're using along the x-axis. Okay, so we sliced these vertically. In the picture that I showed you earlier, we were slicing it vertically. So we're going from 0 to 1, maybe along the x-axis. A couple of things about this integral. First of all, the pi is just a constant. Since pi is a constant, we could factor that out. We could put that out in front of the integral. So we could rewrite it like this. Pi times the integral from a to b of the radius squared times dx. Okay, so we still have the pi r squared there. One other thing we need to point out here is that r is not an x. Now it seems obvious, right? But r is not constant. The radius is changing. You can see here in the stack that I have, you have radii that are bigger and smaller. But this r, we can't integrate this in terms of x. So we're going to have to write this r in a different way. Using what? Using x's, right? So in some way we're going to use that function. When we're revolving around an axis, it's going to be really easy. When we're revolving around the x-axis or the y-axis, it's going to be really easy. When we start revolving around an axis that's like x equals 3 or x equals 2, we're going to have to do a little bit of figuring here to figure out what that radius is. And we'll do an example like that here in a second. So then this is the formula that you need to know. If you're going to find the volume of a solid using the disk method, that volume is going to be given by pi times the integral from a to b times r of x squared with respect to x. Notice here that I wrote the radius as a function of x. So it's saying that we're going to take the radius and square it, but we need to write that radius in terms of x, not in terms of r, because we can't integrate r with respect to x. One other thing I want to point out here is that when we are slicing it, when we're rotating around the x-axis, so we're rotating around a horizontal axis, we're going to slice it vertically, which means that we're going to be dealing with the dx. If we were rotating around a vertical axis, like the y-axis, then we would slice it horizontally, which means that we're going to have a dy involved. And then in that case, if we were around a vertical axis, this would be a dy, and this would be the radius in terms of y instead of in terms of x. So we need to recognize also when we're slicing vertically or slicing horizontally whether we need to use dx or dy.